All right, welcome everyone to another deep dive. Today we're going deep on AI again. Specifically, a new approach to a pretty fundamental problem, actually.
Yeah, yeah, you could say that.
Giving AI a long-term memory, and I mean one that really works.
Yeah, it's funny how good these models are getting at processing information,
Oh, absolutely.
but giving them a memory that's, robust, flexible, and can actually scale, that's a whole other challenge.
It really is.
This paper we're looking at today, Titans, Learning to Memorize at Test Time, it's taking a really different approach to that problem.
It is, and we're going to unpack all that.
Totally.
So first things first, just to set the stage, let's talk about the limitations we're dealing with. Like right now, with existing AI architectures, when we talk about giving AI a memory, what's not working?
Yeah, so, you've got models like transformers that have been, undeniably revolutionary.
Huge, yeah.
But they hit this wall when it comes to really long sequences of information.
Okay, so like length is an issue.
It is, because the way they process, like the relationships between all the data points, it has a computational cost that just explodes as the sequence grows. It increases quadratically, actually.
Quadratically. So like it's not just a linear increase in effort, it
gets way worse,
Yeah.
way faster. Like if you double the amount of information the AI has to consider,
oh, wow.
the effort doesn't just double, it quadruples.
So it becomes really impractical very quickly.
Very quickly, yeah. And then, you have other approaches that are designed to be more efficient, like linear transformers.
Right.
And they manage to get that computational cost down to a more linear increase, which is great.
Sure.
But often the trade-off is that they struggle to compress really long histories into a fixed size state without losing crucial information. It's like trying to sum up a whole encyclopedia in like a single paragraph.
Yeah.
You just lose the richness, all the connections.
The nuances.
Exactly.
Yeah.
And the paper really highlights that, it's not just about efficiency. A lot of architectures out there, from, older designs to even the most advanced transformers, they face issues in adapting to new situations.
Okay.
Extending their understanding beyond the data they were trained on and actually performing, more sophisticated reasoning.
And I mean, this is something that like even small children can do, right? You can show them a new object and they can start to reason about it, even if they've never seen anything like it before.
Exactly. And the researchers behind this paper, they think that maybe something fundamental is missing. Maybe we need to look at how, our own brains handle memory for inspiration.
Interesting.
Because we don't just have one type of memory, right? We've got short-term memory, long-term memory, working memory, all these interconnected systems that serve different purposes.
Yeah.
And maybe AI models are missing those distinct but integrated components, the components that would let them learn from data and build up a deeper understanding of what's happened in the past.
So instead of just scaling up the existing models, we need to fundamentally rethink how they're put together.
Yeah, and that's a key part of their argument. And that leads them to this idea of, like, memory in AI. It's a neural update caused by input, they say. And learning is about acquiring useful memory.
Okay, so data comes in, the neural network changes, that's memory.
Right. And learning is about making sure those changes are helpful later on.
Makes sense.
Now, they contrast how different models handle this. Standard transformers, they're essentially just appending new information to their memory.
Right, just adding it on.
No real compression. But then linear transformers, as we talked about, they try to compress this historical data into a fixed size during those memory updates.
So one's accumulating, the other's condensing, both have downsides.
Exactly. And then they start asking some big questions, right? Like, what's the best structure for memory in AI? How should we update it?
Right. How do we retrieve the information we need when we need it? I mean, these are pretty fundamental questions.
They are. And they go further, thinking about how can we design architectures that have these different memory components like we see in human brains. And they even question whether a single vector or a matrix is enough to represent, long-term history. Maybe we need what they call deep memory.
Deep in the sense of having multiple layers, like a deep learning network.
Exactly. That a more complex memory system could be much better at storing and recalling information over long stretches of time.
Okay, so they've identified the challenges, right, and some core principles to guide the way forward. So how do they actually propose we solve this with this new neural long-term memory idea?
So here's where things get really interesting. They introduce this concept of a neural long-term memory. And get this, it actually learns how to memorize data into its parameters at test time.
Wait. Isn't memorization like a bad thing in AI?
You'd think so, right? It usually leads to overfitting bad performance on new data.
Right, exactly.
But here's the key. They're focusing on the online adaptive nature of this memory.
Okay.
It's not about rote learning the training data. It's about learning a way to remember and forget that actually makes the model better at generalizing to new information.
So it's learning how to remember, not just what to remember.
Precisely. And they do this using a surprise metric, which is actually really cool. It's based on the idea that we, as humans, we tend to remember things that are unexpected or surprising more vividly.
Yeah, absolutely. Like if something really shocking happens, you're going to remember that a lot more clearly than, just a normal day.
Exactly. So the researchers thought, if something's surprising to the AI, it's probably important and should be stored in memory.
Makes sense. But how do you actually measure surprise in a neural network?
So initially, they defined it based on how much the network's internal state changes when it gets new input. Like how much does it have to adjust its understanding of the world based on this new data?
So bigger change, bigger surprise.
Basically. But then they realized that just looking at immediate surprise could cause the model to miss important information later on.
Okay, yeah.
Like imagine you see a car crash. That's super surprising.
Yeah.
But what happens next is still really important, right? You don't just forget everything else because of that initial shock.
Absolutely.
So they improved the metric by adding a past surprise component. It's kind of like a momentum term. It takes into account how surprised the model's been recently.
So the AI is keeping track of its recent surprise level.
Exactly. And the overall surprise is a combination of that past surprise and the immediate surprise of the new input.
Okay.
And they directly compare this to how momentum works in optimizing neural networks, which is interesting.
It is interesting. So it's not just like a static surprise level. It's dynamic and it evolves over time.
Exactly. They also have a way for the surprise to decay over time, depending on the data itself.
Okay.
And a way to control how much the immediate surprise affects the memory update. These aren't fixed values. They can change based on what the model's seeing.
So like if the topic shifts completely, the AI can kind of reset its surprise level.
Exactly. That adaptability is crucial for managing memory properly.
Right.
Now, the memory module itself, it focuses on associating input keys with values.
Okay.
Kind of like attention in transformers.
Yeah.
But it's happening within the long-term memory's own parameters.
Got it.
And they use linear transformations of the input to create those keys and values.
So it's taking the input data, turning it into keys and values, and storing those associations in its long-term memory.
Exactly. And of course, you need a forgetting mechanism, right? You can't just keep storing everything forever.
Yeah. There's got to be some kind of limit.
So they have this gating factor, alpha. It determines how much of the existing memory is retained when new information comes in.
Like a filter.
Kinda. It's similar to forget gates in RNNs.
Right.
Allows the model to selectively discard less important information.
Yeah.
Manages limited capacity.
Makes sense. So what about the structure of this memory? Like what's it actually missed of?
Mostly multi-layer perceptrons, or MLPs, with at least 2 layers. They argue that these deeper networks are more expressive, allowing for more complex relationships to be learned. And their experiments show that this leads to better performance.
So we're going deep on the memory itself.
Deep memory, exactly. And when it comes to retrieving information from this memory, it's surprisingly simple. It's just a forward pass through the memory module using a query derived from the current input. And the memory parameters themselves don't change during this retrieval.
So you build up this memory, and then you can just ask it for what you need.
Precisely.
So far, so good. But I imagine training this long-term memory, especially with really long sequences, has to be pretty computationally intense.
Yeah, it could be. So they figured out how to reformulate the training process using really efficient matrix operations.
Okay.
This is key, because these operations are super optimized for the hardware we use these days, like GPUs and TPUs. Makes training much faster and more parallelized.
So it's compatible with the tools we have.
Exactly. They also talk about using techniques like chunking the sequence and parallel associative scan to speed things up even further.
Processing it in larger blocks.
Right. And they even mention the possibility of making those key parameters, alpha, theta, and eta, dependent on larger chunks of data, which could potentially make training even faster, although they mainly focus on making them token-dependent in their experiments.
So there's a trade-off there between speed and how granular the memory updates are.
Exactly. Now, On top of all that, they have this other really interesting concept called persistent memory.
Okay, this is different from the long-term memory we've been talking about.
It is. This is like a set of parameters that the model learns, but they're independent of the specific data it's seeing at any given moment. It's kind of like giving the AI some foundational knowledge, before it even starts processing the actual input.
So like setting the stage.
Yeah, great analogy. They have a few reasons for doing this. From a memory perspective, it provides a more stable base of information about the task, which complements the more dynamic long-term memory.
Right.
From a neural network design standpoint, it's similar to some data-independent features you find in attention mechanisms.
Interesting.
And technically speaking, they say it can help reduce a potential bias in attention towards the very beginning of a sequence. Leads to a more balanced processing of information.
So it's not just remembering, it's influencing how the AI pays attention.
Exactly. And all of this, the neural long-term memory, the persistent memory, it all comes together in what they call titans.
Titans. Okay, so tell me about these titans. What do they look like in practice?
So they actually have a family of architectures based on these ideas. 3 main variants, actually.
Lay it on me.
The first is memory as a context, or 𝘵𝑚. In this one, they break the input sequence into segments.
Okay.
And for each segment, the model uses it to query the long-term memory. And that retrieved information, along with the persistent memory and the current segment itself, are all combined and fed into an attention mechanism. And then the attention decides what from all that should be stored back into the long-term memory for later use.
So the memory provides context for attention, and attention helps refine what gets stored in memory.
Exactly. It's like this back and forth. And a key point, during testing, the persistent memory stays fixed. Attention is kind of like an in-context learner, and the long-term memory keeps learning and adapting.
That's a really dynamic system.
It is. Now, the second variant is gated memory,
Right.
or MAG.
Okay.
This one's a bit different. It has 2 pathways running in parallel.
Mm.
One uses sliding window attention, so it's focused on the recent past.
Okay.
The other pathway takes the direct input and uses it to update the long-term memory.
Got it.
And then the outputs from those 2 pathways are combined using a non-linear gate.
Interesting.
And the persistent memory is also used in that sliding window attention part.
So one's looking at the immediate context, the other's got the bigger picture.
Yeah, good way to put it. The last variant is memory as a layer, or ML.
Okay.
This is more of a traditional approach where you just stick a memory module in before a sliding window attention mechanism. Idea being that the memory processes the context first, and then attention acts on that process representation.
Seems a bit more straightforward.
It is, but the paper suggests that this might not be the best way to use these 2 mechanisms together. Like, it might not fully exploit their potential for interaction.
The synergy.
Yeah. They also have a version called memory without attention, or LMM, which is basically just the long-term memory module on its own, no attention.
No attention at all.
Nope. They wanted to see how capable that memory module is all by itself.
It's an interesting experiment.
It is. And there are some common architectural details across all the Titans variants, like residual connections, Silu activation, normalization, depthwise separable convolutions, gating mechanisms, the usual suspects. They also have a theoretical result that suggests Titans can solve a wider range of problems than standard transformers and many other modern recurrent models, especially when it comes to keeping track of information over time.
So theoretically, they have the potential to be much more powerful. But what about the practical side? How do these Titans actually perform?
So they ran a whole bunch of experiments across a really diverse set of tasks. Language modeling, common sense reasoning, needle and haystack problems, DNA modeling, time series forecasting.
So a really good mix to test how well they generalize.
Yeah, they really put them through their paces.
What were the results? I'm dying to know.
Well, for language modeling and common sense reasoning, their memory without attention model, LMM, actually did the best out of all the models that didn't use attention.
Wow, okay.
And all 3 Titans variants, MA, MAG, and LL, outperformed other hybrid models that combined RNNs and attention. Interestingly, MMAG and MAG performed similarly overall, but MOC seemed to be better at handling long-range dependencies.
So the more integrated approaches to memory and attention were better than just stacking them together.
Yeah, seems like it. And they both outperformed ML too. Which kind of supports what they were saying about that design.
Right.
Now, for those needle in a haystack tasks, which are specifically designed to test long-term memory retrieval, the LMM model again, outperformed the baselines across all different sequence lengths.
So it can really handle those long contexts.
Yeah. They think it's because of the effective memory management with the momentum and forgetting mechanisms.
Right.
The deep nonlinear memory and the explicit forgetting mechanism compared to other models.
Interesting.
𝘬𝑚𝑡 also did really well on these tasks.
So the memory is good at holding on to and retrieving specific pieces of information from a huge amount of data.
It is. And this is really important for lots of real-world applications.
For sure.
But get this, on the Babylon benchmark, which is all about reasoning over very long documents, Titans, specifically the MAC variant, actually outperformed much larger models like GPT-4 and Llama 3 in both few-shot and fine-tuning settings. And it did this with way fewer parameters.
Okay, that's really impressive.
It is. And it even beat transformer-based models with memory, like RMT, which suggests that this online memory learning approach is really effective. Even adding a retrieval mechanism to Llama 3 didn't beat Titans.
So smaller model, better performance, that's a pretty big deal.
It is. They also tested the effect of memory depth, adding more layers to the MLP. Deeper memory was better, especially for smaller models and longer sequences.
Makes sense.
It did increase training time a bit, but the performance gains seemed worth it. There's always that trade-off, right?
Yeah.
Now, in time series forecasting, their memory module outperformed other models, like Mamba-based, linear, transformer-based, on standard data sets. And in DNA modeling, the LMM variant was competitive with state-of-the-art models.
So it's not just limited to language, it can handle other types of sequences.
Right. For efficiency, LMM was a bit slower than really optimized models like Mamba 2 and gated DeltaNet, but Titans, MAL, was actually faster because of those optimized attention calculations.
Okay.
And finally, when they ablated the memory module, removing different parts to see what happened, every component had a positive effect on performance, especially weight decay, momentum, convolution, and persistent memory.
So all those little details contribute to the overall success.
They do. And again, MA and MAG generally outperformed ML. Shows you there's that balance between speed and expressiveness.
So it really sounds like they've made a strong case for this new approach to memory in AI.
I think they have. The key takeaway here is that Titans introduces this really innovative architecture with a learnable long-term memory.
And it really seems to work.
It does, and it could be a huge step towards AI systems with much more robust and flexible memory capabilities.
Which could be game-changing for so many fields.
Absolutely. I mean, imagine the potential impact on natural language processing, scientific research, you name it.
For sure. If anyone wants to explore this further, keep an eye out for the code release.
Yeah, and seeing how it performs in different applications would be really interesting.
Absolutely.
And, this feels like the start of something much bigger.
I think so too.
There's so much more to explore with this whole idea of memory and AI.
And to leave everyone with something to think about. These researchers took inspiration from human memory, the different types, the role of surprise, all that. What other aspects of biological memory could we use to inspire the next generation of AI?
Great question. Thanks for having me on to talk about this. It's been fascinating.
Absolutely. Thanks for listening, everyone, and we'll catch you next time on The Deep Dive.